So I welcome you, everyone. Today I will be, actually, we will be presenting the theory of relativity. Yeah, we will explore how space and time are not fixed and absolute, but influenced by mass and velocity. So, the theory of relativity is actually divided into two theories: the theory of special relativity and general relativity. I will first explore special relativity. It deals with light, velocity, and reference frames. So let's start with the main ideas. The speed of light is a universal constant. This means that no matter how fast an observer is going, they will measure approximately the same numerical value, c. Now let's talk about time dilation.
Mhm.
Time dilation explains how time do not tick at the same rate for all observers. It depends on the motion of the reference frame, actually, yes. So I will explain this by visualizing everything because it's easier, of course. Okay, one moment. I will share my screen right now. Okay, can everybody see my screen? I ask.
Yes, your screen is visible.
Yes.
Okay, very good. So let's say we have like a train station, and we have an observer M here at the center. Now we have two light beams at each end. This is light beam A, and this is light B. Yeah. We have a train, and on this train there is a person, M prime. Let's call it M prime. Oh, I can. Okay, I'll just try to draw a train. Okay. And we have a person, observer, M prime. When M prime's position is equal to M's position, so they are at equal distance from light beam A and light beam B. A and B will emit light signals simultaneously. So let's see what happens. Let's say M prime is already at the position and M is at rest. What does M see? From M's perspective, the light from both ends reach its position at simultaneously at the same time. But what does M prime see? That's interesting. So the light comes from here and from here. And M is moving at the velocity v. M's prime's perspective is the following. When it reaches M's position, M prime sees the light signal from B reaching its position before light signal A. So this C reaches M prime before this C. We can call it C1, C2. I want to ask if everything is clear because I don't know.
Everything is clear. I do have a small question though.
What is it?
So you said C2 and C1, these are the speed of light, right?
Yes, they are constant. They are the same.
Yeah, so C1 and C2 are the same, right?
Yeah, it's constant.
Thank you.
Okay. So from M's perspective, C1 and C2 reach M prime's position at the same time, which is very weird because M prime says something completely different, and we wonder how is this possible, right? How is this possible? Well, the truth is they are both right. Why? The laws of physics are all the same in every reference frame. They are not different. The speed of light is constant everywhere. So how is this possible? Well, we can see the direction of the velocity v is toward c2. And I don't know if you know about relative velocity and equations, but from M's perspective, C2 is coming at the speed of V plus C2. So M prime sees C2 coming faster than C1 from its reference frame. Is that clear?
Yes.
Do you guys understand
Yeah,
everything?
that's
Okay, that's good. That's good. And we come to a statement where time ticks at a slower rate for bodies that are in motion. And that's pretty much it. Now, this is how Einstein explained it in his first paper in special relativity. Um, his former mathematician geometry teacher, he's called Minkowski, offered him to help him formulate his theory in a better way because for mathematicians explaining things with things like trains and whatever this is was kind of not useless. Minkowski made a diagram explain, explaining the whole thing from a more geometric point of view. So let's say we have a position, we have a space x. This is our space dimension, and we have time, two dimensions, space and time. So let's say we have the position, the changing position of a body in some time interval. Let's say its velocity is smaller than the speed of light. Okay, now let's have the speed of light, of light, sorry, itself. It will look something like that. Now, what does that tells us exactly? It tells us that the speed of light will reach position faster in a shorter time interval, and time will tick slower for it. Do you guys understand it? May I ask once again?
Yes. I understand how the gradient makes sense with the graph, in the sense with position and time.
Mm-hmm. Okay, that's good. Uh, Also, special relativity covers things like the famous equation E equals mc squared, but I will not derive it right now. But we will do that the next session, which is next week, I think. I don't know. So we can go
All right,
and
all right, all right. If you mind if I explain the experiment of time dilation?
okay.
Okay, so now back when Newton gave his laws of motion, he stated that time is the same everywhere. No matter if
Absolutely.
you are in the edge of the universe, the time will remain same as it is on Earth. But then Einstein came and he said, "No, brother, you're wrong. Time is not same everywhere. Time is relative." Now, to prove this experiment, it was not proved by Einstein. Instead, an experiment was done in 1971 by Joseph Havel and Richard Keating, who said that they used 12 clocks in total. They kept eight of them in an aeroplane, if, in two aeroplanes, not one. And both the aeroplanes, one flew in the eastward direction, one in the westward, and the four remained on Earth. And then, after flying for some time in that aeroplane, all the clocks were not even like they all had same time, not even less or more by 1 single second. And when the planes landed, the time of all four clocks of plane were different from the Earth. And that is how time dilation was proved. And there are several things like uh, a Russian, like what do you call, cosmologist, when they sent Roscosmos, sent a person in space in the space station, it is believed that he is 6 seconds ahead from the person born together with. So that is how time dilation works. Are you getting me?
Yeah.
Thank you for that assessment. Um, okay, now Jakshu, would you want to explain general relativity to the rest of us?
He left.
He left. Incredible. I guess I have to explain it. Well, general relativity is kind of more complicated than special relativity, although it looks easier if we visualize it. However, the mathematics are much more complicated. It uses differential geometry and etc. We will not cover that, but it's pretty. I can explain it in simple terms right now. Actually, I will not draw anything. I think in the fabric of space, if a body has mass, the space fabric and the space-time itself will be curved because of the mass of the body. And this theory basically explains why does gravity happen. Newton explained how does it work. Then Einstein came and he explained why. Basically, that's the whole thing. Uh, I can explain it in depth later. I am not prepared right now.
Right. Yeah.
Okay, that's from me. Thank
Uh,
you.
so what is the main like you know how general relativity is based on special relativity? You mentioned that, right? So how does
Mhm.
that work? Like they look completely independent. So how like combine both of
Someone is raising his hand. Also, can you repeat the question?
them?
I didn't hear you well.
So you mentioned that the general relativity is based on special relativity, right?
Yes.
So how does that work? Because they seem to be completely independent and different.
Ugh, well, how do I put this? Uh, okay, how do I put this actually? Yeah. The connection between the two things is, I'm not actually sure. I think it was light.
Right.
Am I allowed to speak?
Yeah, you
Yeah,
can.
yeah.
Oh, yes, I am. Okay. Uh, Kushagra, right?
Yeah, that's me.
So, can I have a go at explaining the theory of relativity, if that's fine?
Yeah, of course. Please continue.
I can? Yay. Alright, so since I see, am I pronouncing your name correct? Is it Paila?
Uh, you pronounce it Giovanni Paiela.
Okay, Giovanni Paiela. Okay, so anyway, I would like to explain it with kind of an example, alright? So,
You are welcome to. Yes.
okay, so imagine taking like a big trampoline, alright, and putting a heavy ball on it. So, the ball would like sort of make a dip in the trampoline and make the trampoline bend down. I guess everyone can imagine that, right?
Yes.
You can. So
Yeah.
general relativity says that planets. So in here, the trampoline is basically the fabric of space time. Are you guys aware of the term space time?
Yeah.
Yeah.
Yeah. So general relativity says planets do the same thing to space time. You know, they actually bend space and time around themselves. All right. So this is
Mm-hmm.
like theory of relativity in a nutshell. Whatever the mathematical term, you know, whatever you want to use it, you can. But I would explain general relativity in like in this term.
Yeah.
Okay.
So from what I read, acceleration and mass, both of them can kind of bend space. And then Einstein said that time is also related to space. So if space bends, time.
Yeah, yeah.
Yeah, and
Basically, according to Einstein, objects move toward one another because of the curves in space-time, not because they're pulling on each other, you know, with the force of attraction. So
yeah,
Einstein supports this theory with evidence, you know.
Yeah.
Although Newton's law is still used for calculations and all, but the theory which is mostly given, you know, calculated is by
Newton
Einstein.
Newton wasn't wrong either because in his book
No, no, no,
Principia,
no, no. For calculations, Newton's law is still used.
no, Newton wasn't wrong. Like I read his book Principia of Mathematica, and it clearly
He
states,
wasn't wrong. That's what. He wasn't wrong. When did I say
yeah,
he was wrong?
no, he stated that gravity exists and how it exists, but he didn't
Mm-hmm.
explain how it works, and he left it to the reader how it works. And I suppose Einstein was one of the readers who came up with the theory explaining gravity.
Makes sense.
Also, the theory was proved right in another experiment when, so you know how if the space-time plane bends, everything traveling straight would also curve around it, right? It makes sense.
That's right. That's right. That's what gravity
Including,
does.
yes, including light, though. Because
Mm-hmm.
ideally, if photons are massless, according to Newton's theory, they would not be attracted by anything. But according to Einstein's theory, if you bend the space-time, then everything traveling on the continuum also has to follow the path. So there's this experiment that was done. There were two stars, right? They took two stars where one star was behind another star, and we could still get the light from the star behind the star, uh, because light was kind of traveling around the star, if that makes sense. Because of
Light was
the
traveling around the star. So you're saying that light was actually reacting to the curves in
not really.
space-time. Is that what you're trying to say?
Yes, yes, that's what I'm saying. See, because it makes sense. Because photons, even if they're traveling around us in a straight line, but the plane is curved, then they'll be traveling curved.
Yeah, so basically objects with mass, somehow influences the surrounding dimensions. And here the dimensions are space-time. So object seems to act as if it can pull on other masses and as if matter weighs down the fabric of space-time sitting on it, creating a curve which like causes nearby matter to slide towards it. Basically you're telling it with the example of light, but anyway, it still
Yeah,
makes sense.
that's what. And, but then there's one more implication of this.
Mm-hmm.
Not only mass, but also acceleration can cause space-time to curve. So let's say,
Yeah, that's what I just said.
yeah, let's say I get I'm a moron and I'm spinning around at very, very high speeds. I don't know why I would do that, but I'm doing that. And
Yeah, that's amazing.
yeah,
Hmm.
and I would end up bending space-time curve and attracting stuff to
Bro,
myself
what?
by just spinning.
Bro, imagine bro starts moving and then space time curves around him.
Yeah,
Kushagra, how heavy are you?
I'm not that heavy, so I gotta rely on acceleration.
Okay. Okay, what else?
I think that's it. Uh, Giovanni, if you
Yay.
are fluent in the derivation that you were telling me about, E equals mc square, can you do that now? We do have some time, right?
I have to do some research, so I have to be sure about the whole thing.
No problem.
Also, about your question about connection between special relativity and general relativity, things like time dilation connects it. For example, time ticks slower when you're in motion, and if you're in a gravitational field, for example, a black hole, your clock will tick slower because you are accelerating and things like that.
Right. That makes sense.
Yes,
Wait, no, I didn't get it. What?
if you're in a gravitational field, for example, of a black hole, and space-time is curved, this
No, but the
will
question was what is the relation between special relativity and general relativity?
now he
Like
has,
basically.
yeah, the connection between the two theories.
Mm-hmm. Mm-hmm.
Yes.
So
So in general relativity, it's called gravitational time dilation.
Okay.
Like, yes, when you're in the presence of massive objects and such, or just in a curved space time.
Yes.
By the way, we have 8 minutes remaining.
Yeah.
So if you have anything to say.
I do not. I don't think so.
Mm. Anyone else?
Oh, wait, I do have one thing to say. It's like about a futuristic technology. We have time on our hands, so I think we can have a small discussion on that.
Okay.
So like you know how we need gravity to sustain life, right? Because you need plants to be in a pot and not floating around, maybe. Uh,
Yes.
yeah. So if we have like you know what a centrifuge is, right? So if you rotate something, then you kind of get a centrifuge,
Yeah.
a centrifugal force that pushes you to the end of the thing. But because we are rotating something continuously, the rotation
Hmm.
is basically acceleration because the velocity is changing, right?
Yeah.
Yeah,
Yes.
it's a vector. So because of that acceleration, what you get is a space-time curve or a simulated gravity. That makes sense?
Yeah, it is such.
So we can,
dude, the best example is when you go for a bath in the bathroom, just fill the bucket, swayed your hands through the water. That shit is fun.
Yeah, that is centrifugal force as well.
Yes,
No,
sir.
what I'm saying is we can sustain life using this technology in space. Like, say you have a huge platform, like a very big plate, uh, rotating somehow, and you're just like standing on it, then you can technically simulate gravity on the end of the plate.
Well, yeah, it's a gravity generator,
Yes, but
literally.
do you
Gravity
think it's
generator.
realistic? Like, is it really futuristic? Possible?
Bro,
Mm, I
that's
think
basically hoverboard.
I think they exist. I'm not sure.
They don't exist yet.
They don't. That's right. What would be the implications of it? That's what I'm not able to understand. How is it useful?
Can you repeat that? Or was breaking?
I'm saying, how is it useful? What are the implications?
You can live in space.
Bro, centrifugal
Basically,
force. How will you live in space? What are you talking?
That's like gravity, no? But in space. Like you can simulate
Huh?
Earth-like environments in space by simulating gravity. Because if you have a thing rotating, first of all, you won't feel the rotation.
Okay.
Because even though the velocity is changing,
Okay, so you're talking upon a bigger aspect. Okay, makes sense.
yeah, not like a bucket, maybe.
Okay.
So we can just like have an environment on the other side. However, it's interesting because this depicts time dilation as well. Like a person standing in the middle technically would feel no gravity, right? While a person standing on the extreme end would have a lot of acceleration and hence a lot of gravity. So you need to like sustain life somewhere in the middle, I suppose. I think they have a specific name for that. Don't remember it specifically. Anyway, I think that's it for today. Giovanni, you have anything to add?
no, no.
Yusra, you have anything to say?
Thank you everyone for coming. Please like and subscribe the channel.
Thank you. Thank you.
Okay.
Yeah. Krishna, you have anything to say?
Oh, it's fine. I was just listening to you all having conversation about all this big stuff and was trying to just grasp the concept of theory of relativity and special relativity. It's really nice listening to all of this and having our mind horizon broadened. Yeah, it was a good session.
Thank you.
Nice.
Okay, then I suppose that's it for